Hello and welcome back to another deep dive.
Hello, everyone.
Today I want to start with something a bit different. I want you to picture yourself in the chemistry lab.
Okay.
Maybe you are standing there wearing that white coat that never quite fits right,
It's a familiar feeling for many, I think.
and you are watching a demonstration. The teacher takes a bucket of dirty, muddy water. It looks terrible.
Right.
Then they take a tiny pinch of these dark, almost black crystals and drop them in.
Just a pinch, yes.
And suddenly, whoosh, the water turns this brilliant, vivid purple.
It is quite dramatic to watch.
It looks like something out of a movie.
Yeah.
And then slowly, that purple fades away, the dirt settles, and the water is actually clearer.
It feels like magic.
It really does, but we know it isn't. It is chemistry. Specifically, it is the chemistry of Unit 4, the D and F block elements.
Exactly. And today, we're not trying to, swallow the entire textbook. We are zooming in on a very specific topic, some important compounds of transition elements.
And honestly, this is the part of the chapter where things finally get colorful. We aren't just memorizing tri-electron configurations today.
Okay.
We are looking at the famous masterpieces of the transition metals.
That's a very good way to put it. You see, for a Class 12 student, the D block can feel very abstract. You learn about orbitals, shielding effects. It's all invisible.
Right.
But these specific compounds, like potassium permanganate, copper sulfate, these are the concrete proof. They show us color, they show us oxidation states, reactivity right there in the test tube.
And practically speaking, why should the listener care right now? I mean, apart from the fact that purple water is cool.
Well, for the board exams, understanding just these 4 compounds covers a huge chunk of the questions you will get from this chapter.
Really? Just 4?
Yes, if you understand the logic of these 4 celebrities, you understand the logic of the whole transition series.
Okay, so let's unpack this. At the simplest level, if transition metals are versatile workers, like we've said before, are these compounds the work they produce?
Precisely. If the transition metal is the artist, these compounds are the art. And we're focusing on the 4 biggest stars today.
Okay, who's on the VIP list?
First up, we have potassium permanganate, KMNO, we'll call this the purple one.
The classic.
Then potassium dichromate, K Herreras, the orange one.
Okay.
Third is copper sulfate, CuSOO, the blue one.
Right.
And finally, we have the iron salts, which are usually green or yellow.
Purple, orange, blue, and green. I want you to close your eyes for a second.
Yeah.
Unless you're walking or something, of course.
Please be safe.
Just imagine. Imagine the transition metals are painters. And because they have these special partially filled d orbitals, they can paint with these vivid colors.
Correct.
Compare that to the main group elements like sodium. They're boring, aren't they? They only paint in white or colorless. But these compounds, this is the real colorful art.
It is. What's really happening here, though, is all about oxidation states.
Okay, the numbers.
Yes. In KMNO, manganese is at +7 oxidation state.
+7. That sounds massive.
It is. It's its highest possible state. Then look at potassium dichromate. Chromium is at +6.
Still very high.
And in copper sulfate, copper is just at +2. The color and the reactivity, they come directly from these high numbers and the d electrons.
So what's the exam-safe definition we should remember, the one to write down?
Certainly. The anchor definition is, important compounds of transition elements demonstrate the characteristic properties, specifically color, multiple oxidation states, and oxidizing power that arise from partially filled d orbitals.
Got it. Now, I want to clear up a common confusion. I used to think the purple color of permanganate was just, decoration.
That's a very common student mistake, thinking the color is just a fact to memorize.
Yeah, KMNO is purple, full stop.
But the purple is a clue. It's not decoration.
Clue for what?
It tells you that manganese is at +7. It means it is desperately hungry for electrons. It is a powerful oxidizing agent.
So the color is like a danger sign.
In a way, yes. Do not just memorize the color. Connect the color to its power.
Okay, I want to organize this. We have manganese at +7, chromium at +6. It's a bit hard to remember the hierarchy. Is there an easy way to rank them?
Yes, think of it like a sports competition, an Olympics analogy.
Oh, I like that. Who wins the gold medal?
The gold medal, no doubt, goes to KMNO, the purple one.
Why?
Because manganese is at +7, the highest number. It's the champion, the strongest oxidizing agent on our list, the most impressive color.
Gold for manganese +7. Got it. So who takes silver?
The silver metal goes to potassium dichromate, the orange one.
Because it's at +6.
Exactly. Chromium is at +6, still very strong, bright orange, but just slightly below manganese.
So +7 is gold, +6 is silver. What about bronze?
The bronze metal is our friend copper sulfate, the blue one. Copper is at +2. It's colored, but it's not as aggressive or powerful as the first two.
And the iron salts, what do they get?
They get the participation certificate.
Right.
I mean, they're very important, but they just shift between +2, which is green, and +3, which is yellow. They're not dominating the competition.
That helps a lot. Gold is purple, +7. Silver is orange, +6. Bronze is blue, +2. Simple logic.
And, there is a reason this concept exists in your syllabus. Without these examples, D-block chemistry is just abstract theory.
Right. It solves the problem of how do we actually use all this theory about electron configuration?
Exactly. These compounds are the practical application. They are the answer.
Okay, let's try to visualize this even more clearly. I'm a visual learner. If I walked into a chemistry museum, what would I see?
That's a great idea. Let's walk through it. Imagine a hall with 4 glass display cases.
Okay, I'm walking in. What's in case number 1?
In case 1, you see a vial of deep, dark purple crystals. This is the purple predator.
Purple predator. Sounds a bit scary.
It is. That's KMNO. Visualize that M+7 ion inside. It is starving for electrons. It wants to eat electrons from anything organic. That is why it's purple and, well, dangerous.
Okay, I'm keeping my hands off that one. What's in case 2?
That's the orange oxidizer, a pile of bright, almost neon orange powder. This is COOO.
Also an oxidizer, so also hungry.
Yes, it's chromium +6, so it's hungry, but maybe a little more selective, a bit more controlled.
Okay, case number 3.
The satisfied blue.
Oh, that sounds nicer.
It is beautiful, gem-like blue crystals of copper sulfate. The copper +2 is calm. It is sitting there, surrounded by water molecules like it's chilling in a swimming pool. It looks nice, but it isn't trying to attack everything.
I like that image. And the last case, case 4.
The shifting iron. In this one, you see 2 bottles. One is pale green, that's Fe+2. The other is a yellow-brown, that's Fe+3. This case just shows how the same metal changes its outfit, its color, when it changes its oxidation state.
This museum idea really helps. Picture the cases, remember the properties.
Visuals stick in the brain much better than just numbers.
Okay, let's go from the museum to the real world. We started by talking about those purple crystals in dirty water.
Potassium permanganate, yes.
What is actually happening? Why does it clean the water?
It is a redox reaction. When you put KMNO in the water, that Mn+7, our purple predator, it attacks the bacteria and the organic dirt. It oxidizes them.
It steals their electrons.
Correct. And here is the cool part. As it steals electrons, its own oxidation number drops. It goes from M+7, which is purple, down to M+2, which is colorless, or MNO, which is brown.
So when the purple color fades...
It's visual proof that the chemistry is working, the predator has eaten, the job is done.
That is amazing. The color change literally tells you what's happening.
We see a very similar thing in the lab practicals with titrations.
Ah, yes.
Yeah.
Staring at the flask, waiting for that one drop to change everything.
Precisely. You often use potassium dichromate, the orange one.
Right.
It actually acts as its own indicator. You don't need to add anything else. You start with orange Cr+6 in the burette. As it reacts, it turns into green Cr+3.
So it's like a traffic light changing color.
Exactly. Orange to green. The color change tells you the reaction is finished. If you see green, you know the chromium has done its job.
Okay, now for a trick question. I've been thinking about this. We talked about the satisfied blue copper sulfate.
Yes.
Is the copper ion just naturally blue?
Yeah.
Like if I found a single copper ion floating in space, would it be blue?
That is a fantastic question, and the answer might surprise you. It's no.
No. Really?
Hmm.
But copper sulfate is always blue in the lab?
That is because in the lab there is moisture, but if you take anhydrous copper sulfate, meaning with absolutely no water attached, it is white.
White, like chalk.
Completely white powder.
So where does the blue even come from?
It only turns blue when it forms a complex with water. Specifically, the formula becomes UHOUO.
Ah, complex formation.
Ah.
That's another keyword.
A very important one. The water molecules, called ligands, surround the copper ion. And what they do is they change the energy levels of the orbitals.
Wait, is this the Davy transition thing?
Exactly. The water molecules create a split in the energy levels. So an electron can now absorb some red-orange light to jump up to a higher level.
And what's left behind is what we see. Blue.
Yeah, you've got it. So the water basically builds the staircase for the electron to jump. No water, no staircase, no jump, no blue color.
Wow. That's a classic exam question, I'm guessing.
It is a favorite. Why is anhydrous CuSO white, but hydrated CuSO is blue? You must mention the water, the complex, and DB transitions.
Okay, this is all gold. Now let's get down to it. For the student with their notebook open, we need the exam-safe clarity lines, the must-know points.
Right. Let's get full marks. Point number 1.
The purple one.
Potassium permanganate, KMNO. You must write that it contains manganese in the +7 oxidation state, and that it is one of the strongest oxidizing agents.
Okay, Mn+7, strong oxidizing agent.
Point 2. Potassium dichromate.
The orange one.
Chromium is in the +6 oxidation state. In titrations, the color change you must remember is orange to green as Cr+6 becomes Cr+3.
Orange start, green finish. Got it.
Point 3. Copper sulfate. CuSOFHA.
The blue one.
The vivid blue color is due to the QHA complex. No water means no blue color. The reason for the color is D-ray transition.
DD transitions. That's the password.
Yes. And finally, iron salts. Feso is pale green, which is Fe+2, while Facet is yellow-brown, which is Fe+3. The color indicates the oxidation state.
And the most critical point of all.
The color comes from DB transitions in the metal ion. Do not say the color comes from the sulfate or the oxide anion. The metal is the star of the show.
The anion is just the spectator.
Correct.
Okay, let's do a quick summary before we wrap up, just to recap the whole thing.
Good idea. The core idea is transition metals form colored compounds because of partially filled d orbitals in variable oxidation states.
And the big four from our museum.
You have the purple KMNO, the strong one, the orange KOA, the titration star, the blue CuSO, which needs water, and the green and yellow iron salts that keep changing.
And the final exam tip.
Remember, high oxidation state equals vivid color plus strong oxidizing power. If you see purple or orange, think hungry for electrons.
High number, high hunger. That sticks. Now, before we go, one last question is bothering me.
Go on.
Zinc.
Ah, zinc.
It's in the D block right at the end of the row. But zinc sulfate is, well, it's boring. It's a colorless white powder.
Yeah.
Why didn't zinc get invited to the color party?
Ah, you've hit on a very important exception. What's the electron configuration of zinc? It's d orbital.
Let me think. Zinc is atomic number 30, so its third orbital would have 10 electrons. 3d.
Exactly. 3d-DAG8, it's completely full.
A full house.
It is a full house. All 10 seats are taken. So can an electron jump?
No. There's no empty seat to jump to.
No empty room upstairs. No d-d transition is possible because the d orbital is completely filled.
Oh, so because it's too full, it can't play with light.
That is precisely why zinc and cadmium and mercury below it form colorless compounds. They sit in the D block, but they don't behave like the colorful artists we talked about today.
That is such a cool exception. The full house rule.
It is a favorite question for examiners to check if you really understand the mechanism.
Well, to our listeners, next time you see that purple flash or that orange to green switch in the lab, don't just stand there. Visualize the electrons jumping, visualize the metals.
Keep practicing, and good luck with your studies.
We will see you in the next deep dive.